Welcome back! Today I want to talk about the basics of serial communication with RS-485, also known as EIA-485, TIA-485 and ANSI-485. RS-485 can be viewed as an evolution or an extension of the RS-422 standard. And incidentally, in late 2021, I uploaded a whole bunch of videos, the basics and the details, about serial communication with RS-422. Whole lot of links in the description. So in this video series, and there will be several videos, you know me, about the basics and the details, I will not repeat everything we already learned about RS-422. Instead, I will reference those videos and only point out the differences to RS-485. Enjoy! Let's have first a look what I've currently set up on the bench. That signal generator is currently churning out a 1 MHz square wave that is fed via that coax cable onto the first breadboard, where the coax cable is of course properly terminated with 50 ohms. Then the square wave signal is fed into that Texas Instruments SN75176B differential bus transceiver, where it is turned into an RS-485 signal, which is then transmitted via that 10-meter Cat3 twisted pair cable onto the second breadboard, where I have another Texas Instruments differential bus transceiver, which turns that differential signal back into a square wave. And of course I have oscilloscope probes connected everywhere. Please note, the two Arduinos are currently just used as power supplies for my chips. We will do some programming later on. Also, I'm using in that chip only the transmitter part and in that one only the receiver part. Here's a schematic of what I have currently on my bench. That's the signal generator generating that 1 MHz single-ended square wave signal that's fed via a coax cable to our first breadboard, where it's terminated by a 50 ohm resistor. And that signal is fed into the D for data pin of our first SN75176B, where we only use the transmitter part. The transmitter is turning the single-ended signal into an RS-485 differential signal. So we have now the signal here on two lines, which come out on the A pin, which gives you the non-inverted signal, and on the B pin, which gives you the inverted signal. And that is then transmitted via a twisted pair to our second breadboard. There it is fed into the A and B pins again. Yes, these are the same pins of our second SN75176B, where we only use the receiver part. And the receiver turns the differential signal back into a single-ended signal. The twisted pair transmission line is terminated on both ends with a 120 ohm resistor. And I provide the ground connection between the transmitter and the receiver by just using another twisted pair in my cable. The differential pair here is usually called like the pins on the chip A and B, while the ground connection between the transmitter and the receiver is called C. The VCC pins of both the first and the second chip, which are fed 5 volts from the two Arduinos, are decoupled with 1.5 microfarad capacitors. That's according to the datasheet. Yeah, not 10 or 100 nanofarads, 1.5 microfarads. And I'm actually using here on my breadboards 2.2 microfarads because I didn't have 1.5 microfarad ceramics. Then we have 2 more pins left. First, the data enable pin of the transmitter. That has to be pulled high, that is to VCC, to enable the transmitter. If you pull that low to ground, the transmitter is disabled and the A and B pin of the transmitter go to high impedance. That is, isolate the transmitter from the transmission line. Second, we have the not receive enable pin here on the receiver. If you pull that low to ground, then the output R is active and churns out the single-ended version of whatever differential signal we're receiving here. But if you connect that to VCC, pull it high, then the R pin also goes to high impedance. By the way, if I lost you with that differential signaling stuff, just watch the basics video about RS-482. Card here, link in the description. Anyway, if we have a look at the oscilloscope, we can see our signals. So first here on top we have the yellow trace. That's the 1 megahertz square wave from our signal generator, fed into the transmitter. And the voltage level 0 is here, is about a little under 5 volts. Then we have the blue trace and the brown trace here. That's the differential signal on the twisted pair of our transmission line. And of course, they use different voltage levels. They flip between, let's say 1.5 volts and 2.5 volts. And all traces are measured to ground. Finally, we have the green trace here. That's the output of the receiver after it decoded the differential signal. And you see we have a nice square wave again, with a little bit of ringing here, but that's an artifact from the breadboard. I'm feeding the signal 1 megahertz directly into a row of contacts on the breadboard, and these rows have quite high capacity. Of course, the output signal from our receiver is again between 0 and 5 volts. So basically we put on one end a nice, relatively nice square wave in. Then we have the differential signal consisting of the uninverted input and the inverted input. And out we get again a nice square wave. 2 remarks here. First, we have a slight delay between the input signal and the differential signal, respectively the differential signal and the output signal. I'm currently measuring the differential signal directly at the transmitter side. So the delay between the input and the differential signal is caused by our little transmitter chip. That's all chip internal delay. The delay between the differential signal and our output signal is logically the sum between the delays on the transmission line and the delay in the receiver chip. And you can see that the second delay is significantly larger than the first delay, which makes sense because transmitting a signal over 10 meters of twisted pair takes some time. Second, if you have seen the first basics video about RS-482, this picture should be eerily familiar because it's basically the same. And if we compare the schematic of what's currently on my bench with the schematic from 2021, when I had the RS-422 set up on my bench, yeah, they also seem to be the same. However, there are some slight quantitative differences and one not so slight qualitative difference. First, RS-422 uses 100 ohm resistors for termination, while RS-485 uses 120 ohm resistors. Second, an RS-485 transmission line is terminated on both ends, while an RS-422 transmission line is only terminated at the receiver end. We will see why in a second. Third, the output of an RS-485 transceiver can be disabled, that is set to high Z, using that not read enable pin. But that's really just a convenience thing for writing software for RS-485. And finally, fourth, the elephant in the room that makes all the difference. The outputs of RS-485 transmitters can be disabled, that is set to high impedance, using the data enable pin, while RS-422 transceiver outputs are always transmitting either a high or a low signal on the lines. Why does that last point make such a great difference? Well, I've here drawn only two halves of an RS-485 transceiver. Here the transmitter part and here the receiver part. And I mentioned before that the output pins of the transmitter are the same as the input pins of the receiver. So a complete RS-485 transceiver looks like that. Meaning a signal can be either transmitted via the differential pair or it can be received via the differential pair. That is, we have here a bidirectional data flow. Though it's only half-duplex, because we can either transmit a signal or we can receive a signal. We cannot do both at the same time. In contrast, the transmitter and the receiver in an RS-422 transceiver are completely independent from each other. That is, the transmitter is constantly transmitting a signal on its own differential pair, while the receiver can constantly receive a signal on its own differential pair. Now, that is of course also bidirectional, though it requires two differential pairs for bidirectional communication. However, it is then full duplex. That is, we can transmit and receive at the same time. Please note, you can only connect a single RS-422 transmitter to a transmission line because an RS-422 transmitter is constantly transmitting. That is, its outputs are constantly either driven high or low. Whereas the outputs of our RS-485 transmitter can be set to high impedance by pulling the data enable pin too low, disabling the transmitter, meaning we can connect several of these to a transmission line. So with RS-485 and just a single differential transmission line, we can build a bidirectional half-duplex bus. That is, we can connect a lot of nodes and each node can transmit on the bus while all the other nodes can receive. Of course, at one time only one node can transmit. And that's also the reason why an RS-485 transmission line is terminated on both ends, because we don't really know where the actual transmitter is at one point in time. In contrast with RS-422, you can either build a bidirectional full duplex point-to-point connection, or you can build a unidirectional point-to-multipoint or multi-drop connection. And that's it. And since there is only a single transmitter in an RS-422 transmission line, you only have to terminate it at the opposite end. Let's talk now about the RS-485 specification. And that specification specifies exactly the same voltages, currents and resistances as the RS-422 specification. In the first RS-422, the basics video, I explained the meaning of all the values in the specification in great detail. So rewatch that video again, because I won't repeat any of that stuff. Instead, we just go over a table here and compare the specified values of RS-422 to RS-485. The first block here is about values for the transmitter, while the second block here is for values for the receiver. The maximum differential voltage between the A and B pins of an RS-422 transceiver with no load is plus minus 10 volts. That's reduced for RS-485 to plus minus 6 volts. The maximum output voltages for the A and B pins measured to ground, again with no loads, are for RS-422 plus minus 6 volts, and it's the same for RS-485. The next two values are for a transceiver loaded up with a transmission line that is properly terminated. So the differential voltage again has to be at least plus minus 2 volts for RS-422, and that is lowered to plus minus 1.5 volts for RS-485. The maximum common mode voltage, so basically the average voltage of the A and B pin measured to ground, is for both specifications plus minus 3 volts. The short circuit output current for the A and B pins have to be limited to 150 milliamps for RS-422, and that is increased to 250 milliamps for RS-485. Remember, RS-422 transmission lines are terminated at one end with a 100 ohm resistor and RS-485 at both ends with 120 ohm resistors. So a total of 60 ohms, meaning we need a little bit more juice to drive a RS-485 transmission line. The maximum delta common mode voltage and delta differential voltage describes how well balanced a differential signal is. RS-422 allows here in both cases a discrepancy of 0.4 volts from a perfectly balanced signal, while RS-485 is more restrictive here, requiring a maximum discrepancy of 0.2 volts each. The minimum input resistance of an RS-422 receiver is 4 kilo ohm. That value is tripled to 12 kilo ohms for RS-485. The maximum threshold voltage of a receiver, so basically its sensitivity, is in both cases plus minus 0.2 volts. The maximum differential voltage between the input pins that a receiver can still handle is for RS-422 plus minus 10 volts. There's an extended range of plus minus 12 volts, but the receiver has only to survive these voltages, not properly work. For RS-485, this becomes an asymmetric voltage range from minus 7 to plus 12 volts. The maximum input voltages at the A and B pins of a receiver measured to ground are for RS-422 plus minus 10 volts, like the differential voltage, and for RS-485 minus 7 to plus 12 volts, also like the differential voltage. I'll put links to some documents into the description of the video, mostly from Texas Instruments, that cover the specifications of RS-422 and RS-485, if you want to read up for yourself. Now let's have a look into the SN75176B datasheet and see how it compares. The differential voltage with no load is a maximum VCC, which is 5.25 volts. So that's okay. The output voltage with no load is also a maximum of VCC 5.25 volts. We are also within the specification. The differential output voltage with a load of 54 ohms is 1.5 volts minimum. So we're golden there too. And the common mode output voltage with load 54 ohms again is between -1 and +3 volts, also within the specification. The short circuit output currents are all within the 250 milliamps limit. The maximum delta common mode voltage and delta differential output voltage are also matching exactly the specification with ±0.2 volts. That was for the driver. Now let's have a look at the receiver. The receiver's minimum input resistance is 12 kilo ohms, so we are golden. And the positive and negative threshold voltage is -0.2 and +0.2 volts. So that's good too. For the last two receiver parameters, we have to look at their recommended operating conditions and their absolute maximum ratings. So the maximum differential input voltage for the receiver is ±12 volts, exceeding the specification. And the voltage range at any bus terminal, so again the input pins, is between -10 and +15 volts, also exceeding the specification. So our little SN75176B meets or exceeds all requirements for RS-485, and it exceeds the RS-485 requirements in a way so it also covers the RS-422 requirements, with one exception: short circuit output current, which should be limited according to RS-422 to 150 milliamps, and our chip only limits it to the RS-485 value of 250 milliamps. And indeed, if you look at the first page of the datasheet, 1 features, it states that it meets or exceeds the RS-422 and RS-485 requirements, which is not completely true because the short circuit output current is only limited to 250 milliamps. Yeah. Let's talk about performance now. The why I've already explained in the RS-422 videos, and the same reasons of course apply to RS-485. In the first RS-422 basics video, I explain how differential signaling is resilient against common mode and differential mode interference. I already carded that video, link in the description. In the fourth RS-422 details video, I explain how the use of twisted pair cables reduces crosstalk and how shielding improves things even more when it comes to interference. Card here, link in the description. With that out of the way, let's talk about cable length versus speed. I've already shown that graph here in the first RS-422 basics video. It has been created by EEGRW and is licensed according to CC by SA 3.0. Link in the description. The blue line is showing the performance of RS-422. I added here a green line showing the official performance of RS-485. And as you can see, they are almost identical. The maximum cable length is 1200 meters, and at that length RS-485 can still transmit 100 kilobits per second, while RS-422 is limited, if we trust EEGRW, to 90 kilobits per second. And if we come with the cable length down to 12 meters, both can transmit 10 megabits per second. Please note that both the scale for the cable length and the scale for the speed are logarithmic. That gives us those nice linear curves here. One example, up to a cable length of 1200 meters, we can transmit with 1 megabit per second. You see the pattern. 12 meters, 10 megabits per second, 120 meters, 1 megabit per second, 1200 meters, 0.1 megabits per second. Another performance point is, of course, how many receivers can we connect to our bus. The RS-485 standard states that you can connect up to 32 unit loads to your bus, where one unit load is equivalent to a 12 kilo ohm load on the bus, which is incidentally the minimum input resistance of an RS-485 receiver. So if you connect 32 unit loads to your bus, you end up with a total resistance of just 375 ohms. And that's in parallel to the two termination resistors. And I think I totally forgot to mention that in the RS-422 videos, but there you are allowed to connect up to 10 receivers with 4 kilo ohm input resistance to the bus. Of course, if you have receivers with higher input resistances, you can connect more. And now let's see if I can indeed transmit a 10 megahertz square wave over that 10 meter of Cat3 twisted pair cable via RS-485. Little caveat here, this is an Ethernet Cat3 cable and it has an impedance of 100 ohm. A real RS-485 cable would have an impedance of 120 ohms. Those we also terminate at both ends with 120 ohm resistors. But anyway, let's try. We're still at the 1 megahertz we started the video with, so let's turn that up to 2 megahertz, looks good, 3 megahertz, looks good, 4 megahertz, let me adjust the time scale a little bit. Ooh, bad ringing here everywhere, but anyway, let's go further, 5 megahertz, yeah. I talked about the ringing, that's really a breadboard artifact. 6 megahertz, now we are experiencing some jitter, but that should be okay. Let me adjust the time scale again. 7 megahertz, yep. 8 megahertz, yep. And you see the flanks of my input signal now get really whooshy here. 9 megahertz, yeah, and definitely jitter, but that's okay. 10 megahertz. 10 megahertz. Over 10 meters of cable. Wow. That's it for today. In the second The Basics video, we will make these two Arduinos talk to each other via our RS-485 twisted pair transmission line. Till then, bye.